The simulation flashed red. Dr. Aris Thorne stared at the resource graph for the Daedalus project, a generation ship designed for Proxima Centauri. His team just found a critical flaw in the aft life support domes. The energy needed for construction threatens to make the entire journey impossible, even before liftoff. Building a generation ship like the proposed O'Neill cylinder would require materials equivalent to 100 Empire State Buildings. These colossal rotating habitats, up to 30 kilometers long and 8 kilometers in diameter, would create artificial gravity through centrifugal force. Such a structure would house tens of thousands, providing a self-sustaining world for centuries. This endeavor marks the first step in humanity's greatest diaspora. Your destination, Proxima Centauri, is only 4.2 light-years away, making it our closest stellar neighbor. This red dwarf star hosts Proxima Centauri b, an exoplanet orbiting within its habitable zone. Though tidally locked, its terminator line might harbor liquid water. This world, however challenging, represents humanity's first realistic interstellar target, drawing us to its distant light. The journey itself would be an odyssey lasting many centuries, perhaps even a millennium, at sublight speeds. Even traveling at 10% the speed of light, the 4.2 light-year trip would take 42 years. For a generation ship, many generations will live and die aboard the vessel before reaching their new home. This transforms a space voyage into a profound human saga across time. Propelling such a massive vessel requires revolutionary technology, far beyond chemical rockets. One leading concept is Project Orion's nuclear pulse propulsion. This involves detonating atomic bombs behind the ship, using the explosions to push it forward. Calculations suggest Orion could achieve 10% of light speed. However, its political and environmental implications are enormous, challenging Earth's very atmosphere. Another propulsion method involves advanced fusion drives, like Project Daedalus's 1970s concepts, burning deuterium and helium-3. These designs envisioned 54,000-ton ships reaching 7.8% of light speed in a little over 6 years of acceleration. More speculative antimatter engines could provide immense thrust. Each option presents its own gargantuan engineering challenge, pushing the boundaries of physics. Maintaining human health over multiple generations in zero gravity is impossible. Artificial gravity is crucial. A common solution is a large rotating section, like the Stanford torus, simulating gravity through centrifugal force. A 1.8-kilometer torus rotating once per minute would generate 1 G. Without this, bone density loss, muscle atrophy, and cardiovascular issues would cripple future generations. A generation ship must be a completely closed-loop ecosystem, recycling every atom of air, water, and waste indefinitely. Systems like advanced hydroponics, aquaponics, and bioregenerative life support using algae and bacteria would be essential. NASA's Milai SSA project already develops these complex systems, achieving up to 98% recycling efficiency. Ensuring perfect long-term balance presents an immense biological engineering puzzle. Preserving genetic diversity within a small founding population, perhaps just 200 to 500 individuals, is paramount to avoid inbreeding and genetic drift. Careful genetic screening and potentially sperm and egg banks would be necessary to ensure long-term viability. This population must maintain genetic health across hundreds of years. The fate of humanity's new branch depends on this careful biological planning. Establishing a robust social structure and governance model is critical to prevent societal collapse over generations. Rules must adapt as new generations are born, whose connection to Earth will be purely theoretical. Maintaining a shared purpose and identity for centuries-long voyages poses unprecedented psychological and sociological challenges. What laws will endure when the founders are long forgotten? The entire sum of human knowledge, culture, and history must be meticulously preserved and passed down through generations. This includes vast digital libraries, educational AI systems, and perhaps even physical artifacts. Imagine the ship's archives holding petabytes of data, detailing everything from art to advanced astrophysics. This vital inheritance ensures the colonists can rebuild civilization upon arrival. Radiation shielding presents one of the greatest engineering hurdles for interstellar travel, especially from cosmic rays and solar flares. Protecting inhabitants from millions of electron volts of radiation means incredibly thick layers of material like water, polyethylene, or even asteroid rock. This shielding could add thousands of tons to the ship's mass. Without it, the crew faces increased cancer risks and genetic damage. The psychological toll of continuous confined isolation on a ship for multiple generations is immense, unlike any past human experience. Crew members would never see a natural horizon, smell real rain, or feel vast open spaces. Studies of Antarctic researchers and ISS astronauts provide some insight, but a multi-century journey amplifies these stresses exponentially. Maintaining mental well-being for centuries demands revolutionary psychological support. Mid-journey, the generation ship encounters a vast, uncharted interstellar dust cloud, far denser than expected, stretching for millions of kilometers. Tiny particles, though individually harmless, could abrade the ship's outer hull over decades, threatening critical systems. The navigation teams would face an agonizing choice: slow down dramatically, extending the journey, or risk structural damage. This unexpected cosmic obstacle reveals the true fragility of interstellar travel. Throughout the prolonged voyage, the ship would need to replenish resources and perform extensive repairs, possibly by mining asteroids or comets. Advanced robotic miners and fabricators would deploy to extract water, metals, and other crucial elements from passing space rocks. These acquired materials would allow for ship expansion, system upgrades, or even building smaller scout craft. Self-sufficiency in the void defines survival for this vessel. Advanced robotics and artificial intelligence would be indispensable for daily operations, maintenance, and even the education of new generations. AI systems could monitor environmental controls, diagnose complex malfunctions, and manage food production with precision. Imagine robotic tutors guiding children through lessons about a home world they've never seen. These tireless companions ensure the ship's continuity and the crew's well-being. An alternative to a multi-generational crew is the sleeper ship, where all passengers enter cryosleep or suspended animation. This method dramatically reduces the psychological burden and resource drain by essentially pausing human biology. However, reliable, long-term human cryopreservation with full revival remains purely theoretical. The ethical implications of waking up in a completely alien future are also profound. On arrival, Proxima Centauri b will present its own harsh realities. It's tidally locked, enduring extreme stellar flares from its red dwarf star. One side faces perpetual day, scorching hot, while the other faces eternal night, frozen solid. The most likely zone for habitability is the Terminator Strip, a twilight band where temperatures might allow liquid water. Surviving this alien environment demands extraordinary adaptability and ingenuity. If Proxima Centauri b proves suitable, even minimally, the next step might involve terraforming, slowly transforming its atmosphere and surface. This monumental task could take thousands of years, involving atmospheric processors, orbital mirrors to adjust temperature, and genetically engineered extremophiles. Such a project aims to engineer a new Earth, but its success relies on unimaginable future technologies and patience. The philosophical implications of severing ties with Earth are profound. The colonists would forge a new, independent human destiny. They would represent a new branch of humanity, evolved culturally and perhaps biologically by their journey and new home. Their connection to the cradle of humanity, Earth, would diminish with each passing generation. This interstellar migration redefines what it means to be human. The sheer energy budget required to launch such a colossal generation ship from Earth into interstellar space is almost inconceivable. Current global energy production would need to be harnessed for years, potentially decades, just for the initial push. This would necessitate a global commitment of resources and cooperation unlike anything humanity has ever seen. Powering this exodus represents an unprecedented engineering and political feat. The dark forest hypothesis suggests that any advanced alien civilization might remain silent, fearing destructive contact, raising questions about potential dangers at Proxima Centauri b. While the journey is for colonization, the possibility of encountering unknown life, microbial or even intelligent, cannot be ignored. Are we merely seeking a new home or inadvertently awakening a dormant mystery?